Hello everyone. Welcome back to Discrete Mathematics, and we still discuss graph here. And in the final part of our discussion on basic terminologies of graphs, I will introduce a few examples of undirected graphs, which are special because it is often appears in the studies or in applications. Um, the first graph, which is actually not very interesting, is the null graphs. The null graphs are the graph with n nodes, so we have any number of nodes, but no edge. So really, the set of edges is empty. So this is called null graph. On the opposite spectrum, you have a complete graph, and we denote complete graph with n nodes by kn with subscript n. So kn is a complete graph, and a complete graph is a simple graph where every pair of nodes are adjacent. So for example, this is k3, so you have 3 nodes, and every pair of nodes in these three nodes are adjacent. This is k4, this is k5, so you see, and this is k10, right? So you see that, and obviously you see here that the degree of phi is n minus 1, yeah, incomplete graphs, yeah, all of them. So that's complete graph. Another special graph is cycle graph. So the cycle graph has n nodes, say u1, u2 up to un, and there is exactly one edge between ui and ui plus 1, and then and also from un to u1. Now, cycle graphs are useful, for example, modeling a topology of a local area network, for example, in the computer network. So here is C3, so you have a cycle, so this is called a cycle graph. This is C4, so this is, for example, this is U1, U2, U3, and U4. Yeah, so you have a cycle graph. This is C5, so U1, U2, U3, U4, U5. So you see that there is an edge between U1 and U2, U2 and U3, U3 and U4, and U4 and U5, and U5 and U1. And this is C10, so the cycle graph with 10 nodes. Yeah. And another special graph is the wheel graph. Wheel graph Wn has n plus 1 node. Remember, Wn has n plus 1 node. And Wn is obtained from Cn, the cycle graph Cn, by adding another node, one node, that is connected with a single edge to every other nodes. So it's like a cycle, like a bicycle wheel. So here is W3, so it is obtained from, this is C3, and then you add one node in the middle. Yeah. So this is W3. This is W4. You see C4 and you add one node in the middle, W5, and then W10. Another spatial graph is hypercubes, denoted by Qn, so, or n cube. So n cube is a simple graph with, remember, the 2 to the power of n nodes. So Q1 has 2 nodes, Q2 has 4 nodes, and Q3 has 8 nodes, and Q4 has 16, and so on, right? Now, the idea here is that each node in a hypercube represents a bit string of length n. So in Q1, each node represents a bit string of length 1. In Q2, each node represents a bit string of length 2, and so on. Yeah, and then the nodes A and B will be adjacent if the bit strings representing A and B differ just exactly in 1 bit position. So for example, 0 differs in 1 bit position with 1. Also 0, 0, and 0, 1, and 0, 0, and 1, 0, so differ in 1 bit position, and so on. Also Q3, you see, for example, 0, 0 differs in 1 bit position with 0, 1, 0, 0, 0, 1, and then 1, 0, 0, right? So 0, 0, 0, and then you see 0, 1, 0, 0 0 1 and 1 0 0. So they differ only in 1 bit position. So you see, it looks like a cube, right? And therefore that's why it's named hypercube. It's hypercube because you could have for example 4. If n is equal to 4, then you have very complicated pictures, even 5 and so on, right? And you also observe that q3 could be obtained from q2 by, so this part is q2, this is obtained from q2, and this, yeah, and you then connect them together by adding the another bit at the leftmost position, right? um, and actually this holds in general, so you get q4 by essentially using two instances of q3. Now you see in our previous example, some graphs have the same, all of their nodes have the same degree. So for example, null graphs have, all of the nodes in null graphs have degree 0. All of the nodes in complete graphs Kn have degree n-1. All of the graphs in cycle graph, all of the nodes in cycle graphs have degree 2. All of the nodes in the hypercubes Qn have degree n, and so on. And these graphs are called regular graphs. So in the graph theory, there is there are results, special results for regular graph. A regular graph of degree k is a graph whose all of its nodes have the same degree k. Yeah, of course, not every n-1, not every regular graph of degree n-1 is a complete graph, because regular graphs may include loops or parallel edges. What is important here is that the degree has to be equal in all nodes. This definition could be extended as well to the regular graphs could be extended to directed graphs as well. Here's an example of another regular graph called Petersen graph. So all Petersen graph, so the nodes in Petersen graph here have, so this is a regular graph of degree 3. So all nodes have degree 3 here. Yeah, this is interesting. If you want to read up, look up the Wikipedia page on Petersen graph, and you will see that Petersen graph, although it's actually not that complicated, it only has 10 nodes and 15 edges, but there are a number of interesting properties that people study on this. I mentioned this here, a few of them. And in fact, we will study Hamiltonian path or Hamiltonian cycles later on. And also Platonic graphs. Platonic graphs represent objects like tetrahedron, octahedron, cube, icosahedron, dodecahedron. This is called Platonic because Plato was the one who first studied these geometric, three-dimensional geometric objects, and these are called then these are all regular dimensional and three-dimensional objects. So for example, tetrahedron has 4. All of the sides are triangles. This is octahedron and so on. So they are all regular graphs. For example, tetrahedron has degree 3, regular of degree 3. Octahedron regular of degree 4. This is of degree 3, and this is of degree 5, and this is of degree 3. Yeah, icosahedron has I believe 10 triangles, and this I believe have 20. Right, so this is the Platonic graphs, and these are also examples of regular graphs. So with this, we conclude our discussion on definition and examples of graphs, and in the next video we will talk about graph operations, as well as after that bipart uh, bipartite graphs.